In this problem, we have the following circuit diagram with an op amp inside of it. We are also given a lot of information that will help us solve for it. For the following question, we have A, B, and C. Each one of these are asking us the same thing basically, just with different values. So we're going to make a general equation for our circuit right here. And after we do that, we can solve for each of our scenarios. So to start our general equation, we are going to start off by listing this as our Vn, the voltage negative, because we have a negative here. We have our Vp, because it's the voltage of a positive, and those are the two terminals of our op amp. Now our Vn is equal to our Vp, and since this is grounded right here, it's equal to 0. Remember, this isn't always the case, but here, since it's grounded, it is 0. So our Vn will be 0. Now we can write a node voltage method for this. We're going to use the node voltage method because we have a node right here. We have some voltage going over this way, and lastly, this way. So in writing our equation, we are going to start with our Vn minus our Vin, and this is all happening over the Rin. Next, we are going to have a plus. We will have our Vn again minus our Vout, and this is happening over our Rf. We will have a plus Vn minus Vout, and this is happening over our C of F, and this is all equal to 0. So this is going to be our equation. Now we know that our Vn is 0, so we can get rid of some of these Vn's right here. And then we are going to combine our like terms. So our V0s, we are going to combine. We are going to have a negative out front. We will have a V0, and then we are going to have a 1 over our Rf plus 1 over our Cf. These are all in the same parentheses, and we're going to set this equal to our Vn over our Rn. And the reason why there's no negative is because we are just adding it to both sides. That way we can get it on the right side. I'm going to move our negative over. So this is going to be the general equation that we are going to use. Now we are going to solve our specific cases. For part A, we know we have a 5 volts right here. We don't have an equation following this. We don't have no cosine or anything. So we have an omega equal to 0. Basically, almost 0, and we'll see what this means in a second. But to solve this for part A, we're going to start plugging things in. We have our V0, and then we are going to have 1 over our RF. Well, our RF is 10 kilo ohms. We will have a plus 1 over our C of F. Now our C of F is given to us right here, but it's not given to us in an impedance, so we have to convert it. We have ZC is equal to a negative J over our omega times C. Well, if our omega is almost, so this is almost 0, not exactly 0. This is basically some really small number. And if we have a big number over a small number, this is just going to give us an infinity. And we are going to get rid of the negative sign because the negative sign is with our j, and we can just bring j down. So it's going to look something like 1 over j omega c. And so now we can see that it's going to be a positive infinity. And that means when we plug this in here, you're going to have 1 over infinity. That means that this is going to be approximately 0, set equal to a negative Vn over our Rin. But we have these values now. We know that our Vin is 5. This is given to us in our part A. It's 5 volts. We're going to divide this by our Rin, which is 10 kilo ohms. So this is 0. We found that. And I'm going to factor out the k's for each of these. I did make a mistake right here. This should not be 10 kilo ohms. This is our R of F, and our R of F is actually given to us as this 20 kilo ohms right here, not as 10 kilo ohms. So we're going to plug in 20 kilo ohms here. Again, the k's will factor out, and now we can multiply both sides by 20 and not 10. And we're going to get that our V0 is equal to a negative 5 times 20 divided by 10. We'll get rid of the zeros. We're going to get that our V0 is equal to negative 10. We don't have an imaginary number, so we're just going to do plus 0 or J0. And this is going to be the V0. So when we plug this in, we're going to have a negative 10 and then a J0. Now we are going to solve for B. B is very similar, except this time we're actually given our omega. So we can solve for our omega. We're going to have V0 in parentheses 1 over 20k plus 1 divided by, and now we are going to find our C of F. Well, our C of F is really our ZC. That's what it should be written as up here. But our ZC is going to be equal to the same thing that we had, negative J divided by, we're going to have our omega, which is 500, times our C, which is 0.1, times the microfarad. So you want this in farads. So it's just going to be 10 to the negative 6. We can plug that into a calculator. And this is going to give us that our Z of C is equal to negative 20,000. Now we can rewrite this as our ZC is equal to negative 20K. And if we do that, we can plug it in here. And this simplification will help us in a second cancel out the K's. This is going to be equal to our V input. So we are going to have a 5. We also have to have a negative out front. And this is going to be over our R input, which is the same thing. It's 10 kilos. So that is our equation for part B. We are going to factor out the K's again. And now we can start dividing things. So combining our left side, we are going to get that our V0 being multiplied by a negative 20. Oh, and also this should be a J. I forgot my J in here. But our Z of C, since it's an impedance, will have a J. So we will have a 20 minus J 20. And this will be divided by a negative J times 400. Set equal to a negative 1/2. Now we can multiply both sides and get our V0 by itself. We will get this as our equation. We can start factoring out, we can start canceling things out. So this is going to leave us with a negative J 200 on top. We can also cancel out the negatives, and we can convert this to polar form. Or what we can do is multiply both our top and bottom by 20 J 20 and multiply this in. This will give us this as our new equation. We can divide this out, and we're going to get that our V0 is equal to a negative 5 plus J times 5. And that is how we would solve for part B. And we're going to write this in like this. In part C now, we are going to use the same equation, again, the general equation, because this is the same circuit diagram. We're just going to have different numbers for our omega, which will change our C of F. Our Vn is the same only because this voltage that we're given is the same. So we can start writing this out. We know that our V0 is being multiplied by the parenthesis with our 1 over our RF, and our RF is 20 kilo ohms, plus 1 over our C of F. Now the C of F is actually a ZC, the impedance, and we need to find it. It's going to be a negative J over our omega, which is 5K in this situation, times our 0.1 times 10 to the negative 6 capacitor. And this is going to give us approximately negative 2K. So negative 2,000 is going to be our answer. And we are going to plug this in right here, surround it by the parenthesis, and set it equal to a negative 5 over 10. And because our Rn is 10 kilo ohms. And now, since everything is kilo on the bottom, we're going to get rid of the kilo, and we can combine this together. That's going to be our answer. And we can now simplify it further by multiplying both sides by the inverse of what is being multiplied by our 20 ohms. So this stuff right here. Now we can multiply both sides by what was being multiplied by our V0 in the inverse. That way we can get the V0 by itself. So we're going to have the negative 1/2. 20 minus 2J should be on the bottom. And we're going to have a negative J 400 up top. We can combine the negatives. So we'll have a positive. We will get rid of this and make this a 200. And now we can multiply both the numerator and the denominator by this. That way we can get rid of the imaginary number on the bottom. We are going to get a J 4000. The J's are going to combine. So we'll have a minus 400. And this is all being divided by 20 squared plus 2 squared. And this will give us 404. And I made the mistake where this is 400, where this should only be 40. Because the 20 times negative J2 only gives us a negative J40. So that is going to be incorrect, meaning that this should only be a 40, not a 400, meaning that when we divide that, it's going to give us a 20 instead of a 200. So not too much is changing. We're just going to be getting rid of a 0 on both of these. So the first is going to be a J400 minus 40 divided by 404. That's going to be the equation. Plugging this into a calculator, we are going to get this as our answer. And that is going to be the rectangular form, or the solution to our part C. And we could write it in here like this. So that's how we would go about solving for this problem. If you want more network analysis problems, there's a playlist in the description. And if you want notes that go over this subject, they are below in a Google Docs linked below the like button.